The point now in these early days is to investigate physical systems of a sort that just haven't existed before. It's to make something that when you see or measure its properties, it's like, wow, atoms have never behaved that way before. Light has never behaved that way before. So the beginning of this is having few quantum things, whether they're electrons or photons or atoms, talking to each other in this quantum language, which if the system is open to the world, there's just too much noise coming in. Imagine you're walking along and trying to have a conversation. So they start talking and boom, in comes a ping pong ball and hits them in the head. And so that constant bombardment disturbs any train of thought about having this conversation in a quantum language. A simple way to think about it is in the quantum world, everything, electrons are not little BBs, little tiny particles, little tiny bowling balls, but they're really waves. It actually goes up and down, just like a water wave. So if you have a nice, perfectly calm day and you're going to put your finger in and then have the waves spread out perfectly calmly, and that's like an electron moving through a solid. But if the wind's blowing, then you get all these other little wavelets that interfere with this beautiful single wave. Well, by the time you're through, you don't see the nice wave. It doesn't have any coherence left. That's famously formulated by Einstein 100 years ago. They called the Fluctuation-Dissipation theorem. If these fluctuations of things coming in to mess up the quantum system, then the atom dissipates its beautiful quantum stuff into the environment. So all you have is just this envelope of energy without the actual waves. And the quantum physics is in the waves. So typically, to have really interesting quantum phenomena, you have to just get rid of all the interactions, all the people out there throwing ping pong balls. You gotta get rid of that.
The shrinking quarter is one of the most popular attractions at the Mag Lab's annual open house. And no wonder.
Combines all the good things of a science project. Light, flash, certain sense of danger, noise, excitement, and yet proves a very important law of basic physics and does something which could not be done in any other way. And it uses a magnetic field.
This cool experiment shrinks a US quarter down to the size of a dime in just 1/1,000,000th of a second. How do we do it? With a powerful machine customized here at the lab, the interplay of electrical and magnetic forces, a handcrafted coil, and the same 120-volt outlet you use to plug in your toaster. First, let's take a look at that coil. It's actually a type of electromagnet. When electricity runs through it, it generates a magnetic field. To make this specialized coil, you start out with
14 gauge copper wire, and we put 10 turns on there.
the magnetic field will be strongest in the middle of the coil, so that's where the quarter goes.
So we use a couple pieces of PVC pipe to hold the quarter in the center of the magnetic work coil. We stack it like that, and then the next step is to tape it together. It takes a while to make each one, and the more precisely it's made, the more perfect the coin comes out. Then we tape that in place, and there's our finished coil.
The coil is ready to go into the shrinking machine, which in a nutshell works like this. When it's plugged into a regular outlet, the machine charges up a capacitor, a kind of battery that stores electricity. In this case, it holds upwards of 7,000 volts, way more than your familiar AA. Some 100,000 amps, enough electricity to power 1,000 homes, will shoot through the coil, way more than it can handle. An explosion ensues, spraying shrapnel through the air and creating a ball of plasma as hot as the surface of the sun. These heavy blocks in a bulletproof box shield spectators from the blast, and for good measure, a bungee cord.
We're going to bungee this box down because the shock wave produced inside there could lift this box right off the platform.
Now it's time to charge up the capacitor.
The whole process takes about 40 to 45 seconds. 3,000 volts, 4,000 volts, 5,000 volts, 6,000 volts, 69, holding at 7,000.
Now Russell flips the switch. Pay attention. If you blink, you'll miss it.
Ready? Okay, here we go. All done.
Did you blink? Here it is again.
Okay, here we go. All done. And there's a lot of smoke and stuff in there right now. You'll see that our coil is gone. It's vaporized, and it's turned into thousands of little pieces of fragmented wire from so much energy going through that wire. So we're going to open it up and take a look at it here. There's our shrunken quarter. Looks like we've got a really nice shrink on that one. Got a lot of detail to it.
The coil has been smattered to smithereens. The quarter, however, is safe in its little nest. The explosion that blew the coil outward also forced the quarter inward. So the quarter retains the same mass, but its diameter has shrunk by a quarter, no pun intended, while its width has grown. So how do you account for this magic trick? The very high current in the coil generates a very high magnetic field in just a fraction of a second. Changing magnetic fields can also induce electrical currents in nearby conductors. This is called electromagnetic induction. So the quarter, made mostly of copper and nickel, begins to conduct electricity too. Because those charged particles are moving through a magnetic field, they experience a force known as the Lorentz Force. The Lorentz Force pushes those particles inward from the circumference of the quarter toward its center. The stronger the current you put into the coil and the more quickly you put it in, the stronger and quicker the magnetic field, the greater the Lorentz forces, and the more the quarter will shrink. From Isaac Newton we learned that to every action there is an equal and opposite reaction. In this case, the reaction to the powerful Lorentz forces pushing inward is the coil exploding violently outward. If you don't get a bang out of science from this demonstration, you won't get it from anything.
Hi, I'm electrical engineer Eric Stiers.
And I'm physicist William Caniglio.
And this is the amazing quarter shrinking machine. This really cool device uses a powerful burst of magnetic field to shrink a standard US quarter
To the size of a dime. As if electromagnetically smashing a piece of metal weren't enough, this demonstration also includes high voltage, a plasma arc, a loud explosion, and stinky smoke.
All of the things that make science fun.
It's also a fascinating illustration of Lenz's law, Lorentz forces, and other physics principles.
Actually, it's a fascinating demonstration of circuits. Switches, capacitors, that kind of thing.
Physics.
Circuits.
Physics.
Circuits.
Actually, we're both right. They're just two sides of the same quarter.
So, I'll go first.
Who clocked your flip-flop? I'll go first.
Fine, let's flip a quarter and let that decide.
Okay.
Alright, I call heads. Heads it is.
Physics.
With all of this high voltage and stored energy, I'm going to need my electrical safety gear. Although the quarter shrinker looks complex, it's composed of only 4 simple parts. A high voltage power supply capable of producing 7,000 volts, a capacitor that can store and release huge amounts of electrical energy, a special switch called an ignitron that releases the stored capacitor energy in one intense burst, and last but not least, our quarter wrapped in a copper magnet coil. Let's see how these work together to produce the giant magnetic pulse that shrinks the quarter. First, the power supply charges the capacitor by placing negative charges on one side and positive charges on the other side. When the capacitor is done charging to 7,000 volts, it's packed full of electrical energy. To get all of this energy into the quarter in one powerful burst, we close the ignitron switch to complete the circuit. The negatively charged electrons on one side of the capacitor now rush through the coil to the positive charges on the other side.
And it all happens in 40 millionths of a second. You can calculate it.
Amazing! Thanks, Dr. Caniglio. Let's watch this again, but slow down a little and zoom out to see what's happening into the quarter coil. When the electricity flows through a coil of wire, it produces a magnetic field around it. That's how you make an electromagnet. When you put 100,000 amps through a coil of wire, you produce a very strong electromagnet, stronger than some of the magnets here at the Mag Lab. But because that field lasts for only a fraction of a second,
40 millionths of a second,
40 millionths of a second, we call it a pulse magnet. The Mag Lab has pulse magnets in Los Alamos, New Mexico, with fields upward of 100 Tesla. So what'll happen to our quarter inside this giant magnetic field? As we like to say here at the Mag Lab, let's do the experiment and find out. Of course, we'll need a quarter. I've already put this one inside a piece of PVC and wrapped wire around it. Let's connect it to the circuit. To contain the explosion, I'm going to stack bricks around the coil and then top it off with a bulletproof box. We'll set the power supply to 7,000 volts. Finally, we're ready to flip the switch that's going to shrink the quarter. Get ready, it's going to be loud and very bright. 3, 2, 1.
Smells like a science project in here. Great job, Eric.
Hey.
I'll take it from here. What was that? Something about the ignitron. Now, that was a blast. But if you missed it, let's see it again, this time in slow-mo. Let's open the box. Oh no, I let out the magic smoke. Eric's gonna have to put that back in. The coil's been blown to bits, but the quarter's still here, somewhere. Here it is. Hot potato! Okay, here it is. Let's talk a little bit about the science of what just happened. We call it electrodynamics, the study of changing electric and magnetic fields. Radio, cell phones, X-rays, light, electric motors, they all follow the principles of electrodynamics. Here are the ones that matter to us today. Number 1, electric currents create circles of magnetic field around them. Number 2 is sort of the opposite of number 1. A rapidly changing magnetic field creates electric currents. And finally, the link between electricity and mechanics. Moving electrons in a magnetic field get pushed sideways. Let's apply that to our quarter. At the start, there's no current or magnetic field around the quarter. But as we saw, when we flip the switch, current begins to create a magnetic field in the coil. It takes 40 millionths of a second, remember? So during that time, it is a changing magnetic field. Now what did we say happens in a changing magnetic field?
A rapidly changing magnetic field creates electric current.
Thank you, Eric. The quarter, made mostly of copper, is an excellent conductor. So electric current begins circling around its edge. We call this effect Lenz's law. Now what happens to a current in a magnetic field?
It gets pushed sideways.
Wise guy. We call that the Lorentz Force. If you keep track of all the minus signs in the math, you find out that it pushes inward all the way around the quarter, which makes it shrink. That's it. So the shrinking quarter is the big story, but plenty more went on inside that box. What about the exploding coil? Well, it's just the opposite of the shrinking quarter, because the electric current is flowing in the opposite direction from the quarter. So when the current in the coil gets pushed sideways, the coil breaks apart outward and hits the walls of the box with about the energy of a gunshot. Now about that flash and bang. At home, if you turn off a light switch, the current stops right away. Here, you can't just turn off the current because it's formed a magnetic field, and the magnetic field doesn't want to collapse very quickly. So instead, as the coil blows apart, it creates little arcs of lightning between the little bits of coil. The lightning, just like in a thunderstorm, accounts for the flash and the bang. Well, there you have it, the quarter shrinker, a great demonstration of electrodynamics.
And circuits.
Well, there is one thing we can agree on. If you don't get a bang out of this demonstration, you won't get it from anything.